All right, welcome back. We are still in Module 2, and we are on Part 2 here, all about energy. And in this video, we're going to look at the how kinetic and potential energy are intertwined with one another when we're talking about an object and the position of that object and the motion of that object. But also, we're going to look at the different equations involving energy and work and how we can calculate energy and beyond. Okay, so kinetic and potential. We're going to see with just this diagram here how these two types of energy transfer and work together with one another. You'll see roller coasters a lot as this example. I use the ball, holding up the ball and dropping it, but here you see up high, right? If they were at the top of this hill and there was no motion, there's already low kinetic energy at the top, but there would almost be no kinetic energy if they were at rest at the top, right, of a roller coaster. But high potential energy, there's a lot of potential gravitational energy that if to the right point, they're going to, use, and it's going to start falling towards Earth. And when that does that, all right, you have kinetic energy. You have this swap here where the potential energy begins to drop. Kinetic energy begins to increase. And so then at the bottom here, they're flying. They're going really fast. Maximum kinetic energy. Tons of motion here. Very low potential energy, especially if this is the ground, right? The position has changed, and therefore the potential energy is dropping when you're talking about gravity. Now, they keep going, and you're still moving. You still have high kinetic energy as it goes about its lower kind of course on this roller coaster, and low potential energy. So low potential energy, high kinetic energy. But you see how these two interplay with each other, and they remain equal just depending on the position of this cart. Okay, they have the same total energy here as here. It's just going to be kind of a ratio, percentage-based deal between potential and kinetic. And what's great about scientific principles like kinetic energy is that there's a mathematical approach that can help us to explain it and visualize it and calculate it and actually apply what is actually going on here. So there's a couple equations that we're quickly going to go through and a little sample problem just to get a feel for what's the deal between kinetic energy, potential energy, and how do we calculate it. So kinetic energy, there's your equation. 1/2 mv squared. So what does all that stand for? Well, you have mass, right? That would be your m. So mass is our m here. Okay, and the v is velocity. So if we're going to solve and calculate kinetic energy, we need a mass and we need a velocity. Okay, so we'll get to a sample problem in a minute. But the next equation we're going to see is for potential energy. And potential energy is equal to m times g times h. And so what's the m? Again, mass. Okay. The g is going to refer to gravity, the acceleration due to gravity, which is 9.8 meters per second squared. That's a constant. Right? That's never changing. Okay? You might see it negative if you're going to consider it falling down to Earth, right? But 9.8 meters per second squared. And then we have height. And remember, with potential energy, height is important because it's talking about the stored energy that it has based upon gravity's influence over that said object. So how high an object is matters in calculating how much potential stored energy that object will have. All right, and the last equation is for work, and that looks like this. F times D. Work equals force times distance. And work, all right, I use the word work and I underline it in that definition of energy, right? The energy is the amount, the quantitative property that needs to be transferred to an object to do work on that object. So if we're going to understand the energy involved in a situation like this, we have to know, well, what is work? And that's basically, from what you see in this equation, it's the amount of force across a distance. So how much force was exerted across a certain distance, that tells you the work. Okay, so let's look at a sample problem for each, and before I do that, I'm just going to label these as I did the other ones: force and distance. But again, let's take a look at some example problems. All right, so kinetic energy. Kinetic energy is directly proportional to the mass of the object and to the square of its velocity. Okay, so let's say that we want to calculate the kinetic energy of let's say a 1,500 kilogram truck. Okay, and it's moving on 270 at 50 meters per second. Okay, so how do we do this? Well, we just plug in variables, right? So kinetic energy should equal 1/2 of the mass, 1,500, times the velocity squared. So that would be 50 meters per second. And we're going to square that. Okay, so now we just need to do some math. So order of operations says that we should do parentheses first, right? So 1/2 of 1,500 kilograms, that's going to be 750. We're going to keep the kilograms. And then we go to exponent. So 50 squared. Well, 50 times 50, that's 2,500. All right. And what happens to the units? Well, they both square. So this is going to be meter squared over second squared. Okay. And then we multiply. So 750 times that 2,500 gives us 1,875,000. Okay, so a big number there. And that is kilograms times meters squared per second squared. Well, guess what? That's a really long way of doing those units. So we got a better way in science. A kilogram times meter squared per second squared. The unit for that is a joule. And I'm going to just change colors here so I can say that all of that is the same as a joule, which is the unit we're going to use for energy and for work. Okay, it's marked with a J. So this will be 1,875,000 joules of kinetic energy that this truck has in its motion right now. All right, so I had to make an adjustment there. I went a little too far down on my workspace there into the potential energy zone, and so I just kind of shifted that up if you notice there. All right, but so we got joules as energy, so let's see how potential energy comes out and how we're going to get to that same unit. Let's say we want to calculate the potential energy of a 70 kilogram boulder that is about 20 meters high, 20 meters up, and it's on a rock face. Let's use a local example. How about Sugarloaf Mountain? All right, I don't know if it's a mountain. It's more like a hill to me. But anyways, there are some rock faces there. Let's say this boulder is sitting up there, and we want to know, all right, how much potential energy does that thing have at that position with keeping gravity in mind? And we know gravity because it's a constant. And so we have all that we need. We have three variables here to then calculate our potential energy. So PE equals the mass times gravity times height. So mass, 70 kilograms, times gravity, 9.8 meters per second squared, okay, times height, which is 20 meters. Again, what do we need to do? We just need to do some math. And so we can go from left to right. We can do 70 times 9.8, gives us 686, times 20, that's 13,720. And notice, what do we have for the units? And I'm going to change back to this purple here so we make sure we see this whole energy change, or sorry, we see this whole unit change. Kilograms, meters, and notice the meters multiply through, so that's going to turn into meters squared over second squared. Same thing as up here. And so we could just say that this potential energy is 13,720 joules. That's our energy unit there. Okay, so that's how you calculate the potential energy of an object. All right, the last one we will take a look at is work and how much work is being done on an object given a force across a distance. So let's say you're sliding boxes into a moving truck, something I just recently did, and you are pushing boxes across the floor of this truck, which is, let's say, 6 meters long. It's about 18 feet. Okay, you're pushing with a force of, let's say, 25 newtons. Okay, what's the work done on the box? work equals force times distance. So we're just going to plug it in. What's our force? 25 newtons times our distance. We're pushing 25 with a force 25 newtons across 6 meters. Well, we just do 25 times 6. That's going to give us 150 Newton meters. What the heck is that? Guess what? A Newton meter is going to be the same thing as, and you know what? I might as well do it. I might as well switch it. Same thing as joules. And that all makes sense because a Newton is really a kilogram meter per second square, because it's dealing with the mass and the acceleration of an object, and then you're adding in the extra meter there, and so you end up getting to that same thing, kilogram per meter square per second squared. All right, and that's the joule. So again, the unit for energy is going to be seen, or work, joules. That's what you're going to be seeing there, or shorthand with just a J. So that about wraps up our conversation around energy, just as far as the introduction, the types of energy, and the equations around energy that we can use to, of course, calculate energy in the real world. In the next videos, you're going to see more about where this energy may have come from originally, and we'll get all into that. But for now, you can practice what you've learned here with a lot of the practice problems and worksheets and resources that are found on the resources page. So check that out. And before you move on, and I'll see you in the next video.